So we're going to start the day, yes? So we're so happy to have Fabrizio Granelli here, Professor Granelli from the University of Trento. As we were saying, I think before, he organized the last two events, last summer, when I was presenting over there, and the one before. So Fabrizio, he's also been, like me, involved for several years in the education board of Communication Society, and we go back quite a while back to talks to schools and visits, and I know that he loves what he does, and of course he also loves his material, which is great. So he will present to you today a lot of good stuff, and I will leave you in his hands for now. And thank you so much for being here, Fabrizio.
My pleasure.
Have a great day presenting, and we'll take it from there.
Thank you very much. So thanks. It's a real pleasure to be here. As Mike was saying, it was a big effort between me, Mike, and a couple of other colleagues to organize this school in the beginning, and we are happy to see that the tradition continues. So I'm very proud to be here and present you some of the, let's say, things that we have been doing the last years, and which probably also impact in the future of communications. So I will discuss today about virtualization technologies and their application to networks, and especially 5G, because now everyone is doing 5G. So why don't we also address this scenario? Practically speaking, I already sent you an email yesterday about where to find the slides. I'm repeating it here. So there is a Dropbox shared folder where there is all the PDFs that I will present today. The main reason for downloading them is that, practically speaking, probably I will not do everything that is written there. So there is more material for you if you are interested to get a little bit more into details. But unfortunately, the link from Dropbox is very ugly. So I hope that I sent you the correct one via email. So hopefully you have already the material in your hands. Otherwise, usually I try to use this QR code to help download the material. So today the presentation will be organized into three sections. We will start with the first one right now, and the first one will be more in general what SDN, what virtualization is. So it will be sort of, let's say, a little bit theoretical. Then we will see in the second section how those concepts can be applied, especially in the framework of 5G. So I will try to give you a glimpse of what is going on in standardization and why SDN, network function virtualization, are expected to play a role in the next generation of cellular networks. Then finally, we have also a couple of hours in the afternoon. So probably in the afternoon, I will finish some of these materials, let's say from the more lecture style presentation. Then I wanted to give you a very small, actually, view of the potential of SDN and virtualization. And to this goal, I also sent you in the same email some information about the software that I will play with while I'm here at the table, that you can replicate also. If you have your laptop, you can replicate it while I'm explaining. I think that it's not a real hands-on session, but it is useful to show you the ease with which you can control the network. So I will show you that in 10 minutes you can set up a network and administer it in the software-defined manner, okay? And if we have some time, I wanted also to show you another important aspect that I will discuss today, which is how you can slice the network. So how you can cut a network into different virtual networks, okay? How you can isolate them. I will explain you for sure the theory. If we have time in the afternoon, I will also show you how to do it in practice, okay? Of course, in a simple scenario, because otherwise I'm also not able to do it. I have my students and my collaborators that are more trained than me to use the software. But my idea is to give an idea that this subject is interesting because it goes easily also to practice. So it is something where you can close the whole loop from designing to simulating, if you want, to the actual deployment. So that is one of the purposes of SDN. That, and I will try also to motivate it today. So before we start, I just wanted to understand if some of you is already familiar with SDN and virtualization. So if someone is familiar, can you raise your hand? Just to get an idea. Okay, so say half of the people. And it's with cellular networks. Okay, there is an intersection, half, but there is an intersection. Okay, good. So, as also yesterday, the previous speaker, please feel free to raise your hand if you have any question. Okay, the idea is that, as I told you, I have more material than what I can present. So, depending on the questions, I can a little bit reformat what I'm presenting. Okay, so if you feel lost, make me know. If you think that you already know very well, and the majority think so, I can skip and go more to other interesting things, okay? So that is what I wanted to discuss today. So there is the first section. Of course, since we have a break at 10, I will not probably finish the first section before the break, but the idea is to give you an introduction to SDN, network function virtualization, how they can be used to really solve practical things, for example, to how to slice the resources of the network, and then some principles on how SDN can be extended in the wireless domain, so that then we are ready for a more, let's say, advanced part. That is the second part where we will go more into 5G specific content. So I will try to explain you why I'm not the only one that believes that virtualization will play a role in 5G, maybe not in the very first releases, but later on, most likely, because it impacts on the architecture. So it has very big impact if we want to achieve the real potential of this. And I will show you some applications where SDN is expected to play a role. For example, to have multi-tenancy in a flexible manner, to achieve network slicing, which is something that I will try to demonstrate. It will be very useful due to the variety of applications that 5G is expected to face. Another thing is about the radio access network. Even yesterday, Anna mentioned the Cloud RAN scenario, so I will try also to elaborate a little bit on that. And finally, there is, in Europe, we have several projects that are connected to standardization in the field of 5G. I'm in contact with some of those, and I will present you the scenario that is expected by one of these projects, which is interesting because it shows which primitives could be virtual in the future. So it presents the practice of what I will face. So let's start from the beginning. So that is, let's say, from let's say the 70s, the 80s, from the history of the internet. I think that is well known. In the internet, you have practically two planes. So you can look at the network from two perspectives. One is the data plane of the network, which is the part of the network, the functionalities, the devices of the network that manage data packets that are generated or sent to end users. So the data plane is responsible for forwarding, fragmentation, multicasting, and other things. So the data plane practically is usually what you are taught when you have a basics 101 networking course. Then there is how you control the network. So from the perspective of the owner of the network, of the administrator, the more important part is the control plane, which is how yourself or your control center can control the functionalities, can configure your network. So in this case, for example, how the routing tables are built, which algorithm I use for routing, or for example, how I handle security, how I handle priority, whether my network is neutral or not, for example, depends on how I manage the control plane. And the thing is that fast forwarding to today, until now, or until some years ago, that was the reference scenario where the nodes of your network used to do both. So a router was, let's say, a member of the data plane, since it was doing forwarding of packets, but also a member of the control plane, because it had control plane functionalities, because the administrator of the network could connect to the router, configure it, and for this reason, the behavior of the network depended on how I could control, which is the interface to control these functionalities. And in the current internet, those functionalities are implemented in the routers in a distributed manner. So every router has data plane and control plane functionalities. The software-defined version, if you want, the software-defined networking approach, instead leads to a transition in terms of the structure of the routers, because the idea is that you detach the control logic, so everything that contains, for example, how you build the routing tables, also how you control practically the switch, is centralized in a single point in the network. There are also alternatives, but in general, the approach is to centralize all the control plane in an item that is called the controller, which can be everywhere. And then to have, let's say, simpler routers that usually are called switches, because they just have data plane functionalities. So the switches become simpler because they don't have anymore the control plane, but still there must be a protocol. For example, OpenFlow is the one that today is gaining much more attention. You need a protocol for the controller to be able to configure the switches in such a way that their behavior in the data plane is the one that the administrator wants. Okay, so you need a secure channel between the controller and each of the OpenFlow switches, if we stay in the names from the OpenFlow standard, that enables to control or even to gather information from those devices. So the approach is that on one side, you will have a complex controller. So the controller, of course, becomes the center of the intelligence of the network. So it becomes much more complex than what we have distributed usually in the routers. But the idea is that the switches will become more trained or more optimized to do what is their job, which is just switching traffic, okay? It is called software-defined networking, or SDN, because you can fully change the behavior of your network by changing simply the logic that you put in the controller, okay? So by software, because the controller is a software entity, you can change completely the behavior of your network. And that is what this term is intended to represent, which represents a very big difference from the past, because in the past, if I wanted, for example, just to change or to add, let's say, a new routing protocol, I would have needed to change or to patch the control plane functionality of all my routers, okay, which requires time, might lead to problems because it's a distributed implementation, while in a software-defined networking approach, all the configurability and intelligence of your network lies in the controller. So you can simply change the controller and add functionalities, and as a consequence, your whole network will change its behavior, okay? So practically, what happens is that you have the traditional network here, where these are three, for example, very unpractical but very simple topology, where you have three routers. This is what we have usually. So every router has control plane and data plane. What we do in SDN is this. So we have data plane only devices, which are these programmable switches that I was presenting before, and then the controller, which is detached somewhere else. The thing is that as I was mentioning before, but this is very important, of course, at the time when you detach a functionality, you need to define a proper API to enable the controller to control the network. And that is what you see in the dotted lines. So you need additional protocols. As I mentioned before, OpenFlow seems to be the dominating one at the moment, but it must be standard, because one of the other features that led to this idea was the fact that to increase, let's say, the speed in developing and implementing new solutions in the network. So the idea is that this part, which is dotted, it will be a single and well-known and standard protocol, so that the companies that build the switches will require your switches to understand only that protocol in order to work. The same for the people that will develop, for example, the controller functionalities. It has to speak in terms of, in this case, OpenFlow. Okay. The other point is that by detaching the control plane functionality, we will have the switches that become dumber because they are not anymore autonomous. I will show you today, if you turn on a system, a network in the SDN configuration, your switches are not able to do anything. They don't know what to do. But since their only job is to forward, practically, and to answer to commands, they can become much faster than what the routers are doing today. The thing is that, of course, the smart part remains in the controller or in the control plane, which is centralized. Of course, that is slower. So I will show you again, even in practice, if possible, that usually the switches will interact with the same periodicity with the controller, but not for each of the packets. Okay, because otherwise, of course, there is no way to work at least at the same rate with respect to the distributed version, because if you always wait for the controller to tell you something, the controller will become very fast the bottleneck of your system. Okay. So here there is also we have to put in evidence this fact that of course we are adding, if you want, some complexity in the network, because we have to add at least one new protocol, in this case OpenFlow, that is the one that will be the core of our approach, because it will be the way to link the intelligence or the programmability of your network with the real hardware, practically. Okay. So there are several definitions of the concept of SDN. And here I tried to convey you the motivation and the basics. Then I will try to show you which are the advantages. This I took from the Open Networking Foundation. So the idea is that you physically separate network control plane from the forwarding plane, so that you have a single control plane software that can control several devices. Okay. In this presentation, I will not enter into detail of the fact that how many or how big can be in your network. Okay, of course, you cannot imagine to have a single controller that controls the whole internet. Okay, for practical reasons. But there are works. I will just show you a glimpse. There are works that enable the same functionality even in a more distributed manner. Okay, don't focus so much on the centralization. Centralization is a logical concept in SDN. So the thing that the intelligence is not fully distributed, okay? But you can have multiple controllers, okay? It's not required to have only one. Okay, at least one must exist, because otherwise nothing will work. But I will show you there are several scenarios where you can have controllers even from multiple companies on the same network. So these are the basic advantages. So the first point is the one that motivates a lot why to use SDN, because it's much easier to control the network. One point is because you have a single point where you gather a lot of information of your network. So it's very easy to process and understand the status of your network, okay? Of course, before you were doing it through control plane functionalities, but here it's natural because your controller will surely interact with all the nodes of your network. The other thing is that it's agile because you can abstract control from forwarding. So the controller will set rules on how to manage traffic, and the switch only implements those rules. Okay, so there is this separation. The logic part is managed by the controller, while the forwarding part is a duty of the hardware, let's say, of the switch hardware. Okay. Of course, centrally managed is what I was telling you before. So consider it logically. So from the logical viewpoint, you need one controller at least. The other thing is that you can, the controller can be as complex as you want. Today we will use a very simple controller, but the controller is a software entity, so there is no limit in the intelligence that you put inside it. And it's fully programmable, so whatever the controller does is completely in the hands of the administrator, okay? And whatever you change in the controller suddenly changes the way your network works, okay? So it's very powerful. The other thing is that, and it's also another reason why companies are, several companies like this idea of SDN, is that if you standardize the protocol between the controller and the switch, then you open the field to a lot of companies, to a lot of vendors, to develop their own solutions. Because, for example, if you will remember the previous diagram, there are three things: the controller, the OpenFlow links between the controller and the switches. By developing this solution, this opens a lot of opportunities for companies because the controllers can be done by anyone. Okay, everyone that a software company can develop their own controller solutions. And if you look in on the internet, you can check. There are a lot of open source available controllers, but there are also proprietary controllers. So some of controllers that are really, you know, you have to buy and maintain them through contracts with companies. The same for the switches. I can build a very simple switch compatible with OpenFlow that can run on a Raspberry Pi, or I can have the commercial switch that Cisco or Huawei or other companies can build. The thing that also was driven, SDN, was also to give more opportunities for companies to invest in improving networks and deploying new solutions. Because as you see, practically, the fact that you have this programmability feature enables to deploy solutions much faster than before. Because before, if I had a network with several Cisco routers with a specific, let's say, software, if I wanted an additional functionality, I would have needed Cisco to come and program or give me a patch for patching all my routers. Here, I just change the controller, for example, or I add a new functionality to my controller. Okay. So let's see which are the applications. Then I will describe a little bit better into details the system. Here I took a list again from the Open Network Foundation. There are several advantages. For example, today we will discuss a lot about the first, which is the virtualization, because the fact that you are introducing the controller makes the controller the core point for the applications to speak with. So you don't go directly anymore to speak with the routers, but the controller stays in the middle and is the one that abstracts the network for the applications. I will show you in the next slide better what I mean. So practically, it doesn't matter how your network, how it is connected, but it is relevant how your controller or what your controller allows to do on the network. The other thing is orchestration, because of course, with the central viewpoint, you can orchestrate the changes in a much better fashion than just in a distributed manner. Of course, programmability is the other thing that is connected to this. The thing is also, it was demonstrated that it can support up to a given limit dynamic scaling. So you can improve your physical part, your components of the network without requiring big changes, because they are just new devices that will be connected to the central controller. And this leads also to a big advantage in automation, because having a single controller helps you to deploy and to maintain the behavior of your system, and also to monitor your system. It's a feature that is also connected to this, for example, to visibility and performance optimization. So the fact that you have a central rule or a central item that manages your network allows to implement some solutions that maybe in the past they were only on the paper, because I could have proposed a very nice approach to optimize my system, but in several cases the reviewers would say, okay, but how can you implement it in a distributed manner? So you need to introduce a new protocol and something like this, which is usually a limitation of several things that appear in the literature. But in this case, you start to have, at least logically, a central point which controls everything. So you can assume that you have a very big and concrete vision of the behavior of your system, okay? I'm not saying that before it was impossible to do the same thing, but this approach can facilitate it, okay? Before, for example, I could have a central vision of the behavior of my system, but if I have, let's say, half Cisco devices and half Huawei devices, I would need a control center that is able to speak with both in the right way, because they usually behave differently, they are controlled with different parameters, they have different functionalities and so on. In this way, instead, you have some basic functionalities, and everything that you add, it's added through the central controller. So this is quite powerful. I will show you also this point later on. So you can share the infrastructure. This is very important because you know that today the companies that are running the infrastructure are suffering because of small or reduced economical revenues with respect to the over-the-top players. One of the points where there is always the issue of network neutrality, things like that, derives from the fact that the people that own the infrastructure are not able to get enough, let's say, dollars out to manage and extend the infrastructure, because traffic is growing forever. So it will never stop. So these people have to build, and increase the capacity or manage better the resources. Multi-tenancy can be a good solution to avoid that every company build its own infrastructure. Okay, I will show you how this can be done in the case of cellular networks, but of course, in wired networks it's even easier, okay? We did it practically, so I can tell you this is like some weeks of work, and you can have open the infrastructure to everyone. Of course, it's also open because, as I told you, the interface with the switches is standard, or it will be standard, and so whatever you want to develop, you develop on top of the controllers. The controllers, I will show you now, they will have two interfaces practically to be programmable, and I will get in a minute to this. The other thing is that if you have a unified vision of your network, and then you integrate this with other information from your computing resources and storage resources, you achieve again a complete virtualization of your network. So you can have a very fine granularity, with a very fine granularity, a high level of control on how you allocate the resources to each of the services, okay? Which is another point that comes in the picture when you want to optimize your system behavior, okay? So let me show you what is the future vision if we go along this way. Practically, this is what a software-defined network looks like. So practically, you have, this is the actual network, okay? So this is the topology. The blue is the topology of the network, so the switches and how they are connected. Then you have, here it's called in general network operating system, but can be a single controller, okay? So the orange one is logically the central controller of your network. Sometimes it's called network operating system because it's the core that controls everything in the SDN. This, which is the controller, offers what is called the southbound interface, because it's to the south, which is, let's say, OpenFlow, okay? That is the control protocol for controlling the switches. But if you see in this picture, there is also a northbound interface, which is the interface that your controller or your control plane will offer to applications in order to be deployed in the network, okay? These two interfaces, southbound and northbound, are different. The southbound interface today is OpenFlow, okay? There is no other alternative at the moment. On the northbound, there is a lot of discussion. There are several languages you can use. There are XML-based interfaces. There are other netconf or other approaches. The idea is that your controller will offer one or more, because it can offer also a set of options for the applications to speak with the controller, because the application will need to say, I want, for example, an application can also be a routing protocol, for example, okay? Can be Dijkstra protocol. So I need to know where are my routers and which is the cost of the links. And the controller will answer with the topology of the network. They can be also different from this. The controller will decide what to show. Then the application runs, and it will tell the controller, that is what I believe is the optimal routing, okay? Then the controller will use this information, for example, to control the switches, okay? It can be a very core functionality. Another application can be security, or security-based, or even a true application, I mean, a service itself, okay? So that is how you detach the physical part from the application viewpoint, okay? That is where you start seeing the virtualization, because what the application sees is not the physical part, the true physical structure. It just sees what the controller or what the network will export, okay? So maybe the network doesn't want to know that there is this switch, because it's used for other things. So it will report to the application only this topology, okay? It's a choice. It depends how the network manager, of course, it's not, let's say, artificial intelligence right now. So it will have some rules from the network administrator on what to export and what not to export, for example. So just here, there are several slides that summarize the things that I told you. So on one thing, you have the hardware forwarding abstraction. So you use low-level primitives to teach to the switches what to do. It will be the core today to show you at least these functionalities even in practice. Then, of course, the presence of a centralized control plane or network operating system or controller allows global network view abstraction. So the controller can export a simplified version of the network depending on the purpose of the application or the decision of the network administrator. And then, of course, the core is the controller or the network operating system, which is the one that maps the commands, so what the apps would like, into low-level configuration of the switches. Okay? For example, I might have an application that tells me that it wants to deliver packets with the shortest latency. For this reason, the network operating system will try to find the path where there is available bandwidth and the shortest possible, okay? This can be a possibility. It depends how you split the intelligence between the applications and the controller itself. As I was mentioning, the good point is that the controller can fully operate on the physical infrastructure to change the behavior. So the applications need to run only once. Let's say that if I want to have Dijkstra in my network, I don't need to implement Dijkstra in each of the switches or the routers, but I can implement it on top of the controller because it's a functionality that I add. If later on I don't want Dijkstra, but someone else came with a very nice new routing scheme, I just change the application, okay? There is people that predicts that for network administrators, the highest level will become like the App Store of Apple. So I want this, I take it, download it, I add it in 10 seconds, and my network changes. Okay? Of course, it's an extreme version. But there is a very strong analogy with what we are doing today when we program a PC. I think in this room, I mean, maybe I'm wrong, but a very big minority of you program in assembler, okay? Can someone program in assembler? I could do it when I was young. Why? Because in the first PCs, you needed to know exactly how the hardware was operating. So if I wanted to change the color of a character, I needed to go in the location in the memory where there was the color behind it, okay? And I would say, okay, this becomes yellow. In another PC, it was different, the way to run it, because the CPU was answered to different commands. But today, instead, we are programming with so high-level languages that we don't even care if they run on one PC or in a cloud, okay? That is exactly the same, but for a network, okay? Of course, it is a little bit different culturally, maybe to understand this, but the idea is that today we have a bashing independent language, so whatever, I don't know, Java, C, you can go SI, Python, they run on all machines, practically. Maybe there are some differences, but let's say they are minor. So whatever PC I want, very easily. And for example, the memory, I don't care how the memory is organized. Okay, for you it will be maybe a shock, but if you look, I have a big book like this. When there was the Commodore 64, you know, it was my first PC when I was young, and I liked to program it a lot. There was a book like this explaining you every location, the meaning of every location in the memory. And it was different, so there is one for doing this, one for each of the pixels in the video, and so on. But now we don't care. We say, okay, plot a circle, or maybe draw a 3D sphere, okay? That is because today everything is abstract, everything is virtualized. The same approach is SDN in the network. So you will not know anymore that is a Cisco switch, or it's a Huawei switch, or it is just a software switch, because I can run it in a virtual manner, as I will tell you again today later. But this allows you much better ways to develop new solutions, because you don't care if Cisco will change the operating system, unless they change OpenFlow. Okay, that is another point, because OpenFlow is still evolving. So today there are several versions available, so I cannot tell you that it's fully standard. But the idea would be that at a given moment, OpenFlow will, let's say, stop the evolution to get a reference for all the hardware, okay? And that is basically why you can achieve virtualization, because at the end, through the controller, your network becomes like a piece of software. You don't want to know how it exactly operates, but you want to know what are the functionalities that it offers to you. Okay, bandwidth, delay, maybe storage, computing, you can put everything inside. Of course, there are standards. Then I will speak about OpenFlow. Here is just to mention that there is a lot of attention because in this, to achieve SDN, you need rigorous standards, because otherwise everything that I told you will be useless, because if you don't have the right standards and the right architecture and a common architecture for everyone, nothing will work anymore. So here, for example, I'm bringing you a little bit more of detail just for your information from the Internet Research Task Force. There is the SDN research group, and if you see, they agree with the basic abstract version that I presented you before. This is much more technical, but you can see that there is, this is the network. What you achieve through OpenFlow is that you have an abstraction layer, because practically you don't care about the exact hardware, but you care about the interface. So that is the meaning of that yellow part. Then you have the southbound interface. In this standard, they split between management and control, but it can be the same if you want. Then you have the northbound interface, and in this case they predict, they will standard actually, the way to describe how to abstract the network services, okay? So that to show you, if you look here, that diagram logically is this one. Okay, this is a little bit more precise. The other is sort of an abstract explanation. So if you are interested, you can check the advancement that they are doing here. Let me start before the break, because I think we have 15 minutes yet before the break, to explain you how OpenFlow works. I will try to teach you some simple things, but just to understand how you abstract and how you can control the switches. So OpenFlow is based on the concept of flow, okay? It comes from the name. Because every switch has inside it some tables, that are called flow tables, that decide how that packet, how each packet potentially is managed by the switch. Those tables are controlled by the controller, okay? So practically, what happens is that you have two ways to use OpenFlows. They can be also used together. One is you turn on your switch, and the controller will write in a proactive manner in the flow table. Okay, so you turn on the switch. The switch, of course, when you turn on the switch is a dumb device, so it doesn't know what to do. It will check where is the controller. The controller will answer and tell him, okay, get this table, now you can do your job. There is another way to do this, which is reactive. That is, you start with an empty flow table, okay? And in practice, when the flow table is empty, several switches operate like normal Ethernet switches, so they can do something. But let's assume that they don't do anything at all. When the switch receives the first packet, it will contact the controller and give the controller some features of that packet, which are practically the ones that you see here, so that the controller can set up a new rule to write in the flow tables. Okay, so every new flow coming in the system will be subject to a decision by the controller, which is like an admission control, sort of admission control, because the controller can say, okay, you drop this flow, simply. How this is done? It is done through a flow table that is very simple. There are header fields, which are, now I will just describe you what they mean. Probably you can guess it, but just for completeness. Then there are counters to know how many times this rule was used. And then there are the actions. Okay, practically you need at least this and this. Okay, and this is what OpenFlow writes or issues to each of the switches. For example, imagine you get a new flow. The controller can decide how to manage this packet, but not just in the switch that told there is a new flow, but in all the network. So, for example, it can decide to set up a specific path for this packet, okay? Very simply. These are the features. So, of course, it depends which port you get the packet in. This is, as you see, it operates in a cross-layer manner. So it uses features from different layers. Okay, this is physical, so which is the port that you received the packet, which is the Ethernet source, the Ethernet destination. If there is a VLAN, of course, it can operate transparently. The controller can decide just to, let's say, re-implement the VLAN inside its network. In terms of ID, this is the number of the VLAN, this is the priority. Then there is, of course, IP source and destination, because you need to know where the packet is going, which protocol is transported in IP, which is the type of service. So here it's a very good news, because this old parameter in the IP field that was never used practically, a little bit in diffserv, but now it comes to be used if necessary, okay? And then you have the transport ports, source and destination ports. Because the switch can operate also a little bit like a firewall, so you can say this application will not get through, okay? And that is how the flow table will look like. Of course, you have a column for each of the features. And it's quite sparse usually, because if you don't set up too many rules from the controller, for example, the example controller that I will show you, it will just operate like a learning switch. So it will just tell the switch just to send it in the other port, for example, or broadcast the packet. Here there are some examples, so you can filter on a piece of the MAC address of the destination, the first line, and here it says that you have to forward it to port 1. Or, for example, you can filter based on the IP on the net mask. Here they're using the first 16 bits of the IP. This goes to port 2. For example, I don't want, it's just a fake rule if you want, but I don't want packets that go from 21 to 21 to get in the system, so they will be dropped. Okay, here I don't, it's an example. There is also the possibility, for example, if you receive a packet with this protocol in the IP field, this is sent to the controller. So you can also, the controller can also say, okay, if you get that specific packet, please ask me what to do every time. Or sometimes it can be intended for local delivery. Local means that the packet goes through the local stack of the switch. Because maybe it's a command, okay? It can be something that can be used for the switches to exchange maybe the status of the link, let's say. Maybe they want to exchange this. It is possible, okay? So what happens is that I'll not comment all of this, but that is the typical flow chart of what happens when a controller, when a switch, sorry, when an OpenFlow switch receives a packet. So first of all, it will start looking at the input port, Ethernet source, Ethernet destination, and Ethernet type, and assume the other are 0, because if Ethernet type is that one, then it's a VLAN packet, so it gives priority to VLAN, okay? If it's another kind of packet, so if it's an IP packet, then it makes, this is, I think, ARP packet, and this is the common IP packet. So depending on it, it selects the right feature to consider. At any time, if you see, this is a separate flow. So if it doesn't find any match, the packet is sent to the controller. Okay, so at the beginning you don't have any table, so it will go to the controller. After a while, you populate, and you will check all these things in parallel. Okay, in the recent versions of OpenFlow, the tables are interconnected, so there can be loops also. It's very complicated. You can build very complicated rules that can be applied in series or in a loop or recursively. There are a lot of ways to do it. But the principal idea is this one. So you have to look up. This is the main action. When you get a packet, you look, depending on some fields, if you find a match in the flow tables. If not, the controller will tell you what to do, okay? And here there are some examples of what you can count. This is important because this is some information that the controller can retrieve from the switch. In the new versions of OpenFlow, I think 1.4 and maybe 1.5, there is a lot of more features, because of course, based on this, the controller learns how the network is doing, so it can react to situations. For example, for each table, you know how many packets lookups were done, how many matches, how many active entries exist, so how many routes were used. Or you can have measures for each of the queues, where you enqueue packets, for each of the ports, for each flow, okay? You can get all this stuff. So you can check, for example, if you get drops, if you get errors on the links, and things like that. So it is quite powerful, because that is what the controller can learn from the state of the network. And that is what you can do, which are the actions that can be employed. So the usual action is the big one, which is forwarding. Okay, the switch is built for forwarding, so that is what you have to do well, and why there is a lot of parameters. Usually, the forwarding rule is between a physical port and another physical port, or you can also have virtual ports. So your switch can have virtual ports because maybe you want to send to the same port but to different queues, for example. So you can virtualize also inside the switch its behavior, and that is what you can do. So you can forward to all interfaces, you can forward to the controller. By the way, I forgot to tell you at the beginning, we will see it later, but the connection between the controller and the switch is done using SSL, so it's a secure TCP connection, okay? So when it's sent to the controller, it means that that packet is encapsulated in a TCP segment, encrypted and sent. It's SSL because of authentication. You know, there are several features. Otherwise, your network, the security would be very low, okay? Still, it has security issues, but let's say at least they start having a reasonable way for communicating. Local, as I was mentioning before, it's a packet that goes to the internal protocol stack, so it can be something for the switch. Table, of course, you can select to perform action in a specific flow table. You can send it back. Okay. This is, for example, in practice, commonly when you buy an OpenFlow switch, it operates in normal mode. So it works like an Ethernet switch. Okay, it's doesn't do anything rather than learning. In the example that I will do this afternoon instead, we will assume that the switch is even numbered, so it doesn't do anything per se, but asks everything to the controller. It's not mandatory because you can have a switch that has an empty flow table, so it doesn't do anything at all. Then, of course, you can use, for example, there is flooding, where you use minimum spanning tree for flooding some information to other switches. Then you have other functionalities. The drop, of course, it doesn't require any explanation, but there is this is interesting. So you can enqueue a packet to a specific QoS queue so that you can control the bandwidth, for example, that you allocate in output. Okay? That is something that, of course, commercial routers do, but the thing is that here you can control it centrally. Okay? And then, of course, you have this, because otherwise your router will not operate as a usual router, because, for example, you need to modify some fields. For example, at least to reduce the time to live, it's a common rule in the internet. So your device, of course, can do this, can change VLAN tags, can change type of service, and so on. So it can operate as common routers do on the switches, on the packet parameters. Here there is, and then we will break. It's a good point to break, actually. Here there is a little bit more of information, which is a summary of what I was telling you. So, but basically the behavior is you get the packet, then there is that flow diagram that tells you that packet will go through several checks. If they fail, you send it to the controller in such a way that the other packets with the same configuration will not be sent to the controller again, okay? So the idea of flows is very abstract, but the thing is that a flow is a combination of these parameters, okay? So when you send the packet to the controller will decide which are the features that characterize that flow, and then it will issue a command to write in the flow table, so that all the packets that will have the same setup will get the same, let's say, execution or the same management. Why? Because if you do the experiment, we will see it today again, hopefully. The first packet of the new flow that you even if you do a ping, for example, I want to ping from host 1 to host 2, and there is in the middle an OpenFlow switch, when you send the first message, if the table is empty, you will see that the delay in the ping is much bigger, because the controller needs to process, first of all, to receive the packet, to process and to send back the answer. So if the controller is far away, it will take maybe even hundreds of milliseconds, okay? That is why you don't want, the controller wants to set good rules, because otherwise it will receive a lot of questions, okay? And that, of course, it's a bottleneck in the system. There are ways for benchmarking how many requests per second you can send to a controller, because also it can suffer to denial of service attacks, okay? In a similar manner as usual things. Of course, another nice thing that not many people maybe catch is that, for example, it's very interesting to have the controller, because the controller can help a lot on the mobility part. Because if the controller learns that you are moving, then the network adapts to you automatically, because you only need the controller to change the route, okay? Which is, involves a lot of problems. The handover process is very complicated. In this case, of course, it must be a functionality of your controller. It's not by default. If you can implement this functionality, mobility becomes very simple. Because if you know that your user is moving, the switches will tell you, for example, then you can change the path accordingly. Last thing before the break, as I told you, there is a secure channel. I'm not saying that there are no security issues, because if you are an expert in security, I believe that between SDN and the smart grid that yesterday was presented, you can become rich easily if you are a very good expert, because there are a lot of problems that can arise. But at least I wanted just to tell you that it's not information that is sent, let's say, in clear and without authentication, because if you use transport layer security functionality, at least you authenticate, so the controller is authenticated with the switch, and the transmission is encrypted, okay? Last thing is this one. OpenFlow allows to use both of these models even at the same time. So you can have a proactive model, so you can send flow table entries beforehand, like usually when the network manager turns on the system, it will have set up everything that you can do. You can instruct your controller to configure everything, or like in this case, use the traditional way, which is the send on demand, which is reactive. So every time a new flow comes in, dynamically you decide, the controller will decide how to manage this. But they are both active at the same time, so no one neglects you from pre-programming the switches through the controller, and also enable dynamic adaptation of the flow tables, okay? So that is, I will show you today, it's very simple. You can issue yourself a command, okay? So if I'm a network manager, I can tell the switch, okay, whatever happens, send a broadcast, okay? Whatever packet you receive, send a broadcast until the controller will tell you something else, okay? So I don't know if there are any questions now, before the break. Yes?
A very fundamental question. Why are we doing this now? So what was wrong with the technology? Like 20 years ago, that we couldn't separate the control from the data?
Very good question. And it's very common questions. Of course, I'm not, and relatively tough to some extent, if you want. The thing is that I'm not telling that these things you couldn't do before, even though I will show you that some things you couldn't. But before you could do them if your routers could do it. For example, let me give you an example. If you build a network at home, at your home, okay? So maybe 2 switches, something simple. Can you assure that one of the flows, for example, you have Netflix, so you want, I don't know, to download a video at 5 megabits per second, something like this, let's imagine. Can be even less. can you assure that that flow will get 5 megabits per second with home equipment? The answer is most likely no, unless you are so good that you put maybe OpenWRT or some new functionality that can control the queues in your switch to ensure quality of service. In principle, I could do it if I buy Cisco switches or Huawei or whatever. If I can configure them well, I can do it. I can do it for sure. I'm not saying that it's impossible. But in this approach, you can do it with devices of anyone. Okay, so the difference is in SDN is that you can still do the things that most of the things, not virtualization in the sense that I will tell you probably, but you can do a lot of the things already. But the problem was that they were vendor specific. So if I know well Cisco, I can have a very nice QoS network from using Cisco devices. If I put a device from Nortel, let's say, everything screws up. It's the practice. I'm not a technician, but if you ask technicians, they will always say, I want always from Cisco, everything from Cisco, everything from Huawei, because they speak the same language. With SDN, you have the advantage that this logic goes higher, at the higher level, in such a way that you don't care anymore which is your hardware, because the functionality is implemented through a common language, okay? So in principle, I can build a QoS-oriented network with building a switch on a Raspberry Pi, given that it can answer, of course, to these commands, okay? So the difference is not much in the functionality itself. You can do also VLAN. I mean, in fact, it is in the slides later. When I will show you the practical example, someone would say, okay, you can do the same thing using virtual LANs. So why should you bother building a controller and doing this stuff? Yes, you can, but in that case, the logic is decentralized. So in order to do this, you have to go in each and other switch and tell each of them, there is this VLAN, please do this and that and so on. In this case, you have the advantage that you can do the same thing, but in a central way. So you tell the controller, open the VLAN. Okay, that is, I mean, I don't want to say that before everything was a crap. It's still, it is still maybe an option. Maybe in the future they will not use SDN anymore. They find something else. But it's a good way because it starts from the detachment of the control plane from the data plane allows you to have a standard interface between the two. Okay, before it was not possible. So I will show you that when we were in 2008, actually, I was already collaborating with Mike, and you remember my former student Dimitri got the idea to detach to move the acknowledgement generation from the mobile system to the access point for several reasons. I will show you the paper if you're interested. In 2008, okay, so there was nothing like SDN in perspective. You know, the feedback that you get from the reviewers is, why should you do it? You have to build a new protocol for doing this. You are changing the behavior. So how can you scale up? Because you need to change all access points to have these functionalities, which is true. I mean, in fact, it remained, you know, a theoretical work. We demonstrated that it could give advantages, but no one used it in practice. The reason was that there was the main reason for, I'm not saying that it would solve all the issues of the world, but the main reason why the people didn't accept, and it was right, was that we were introducing, let's say, a lot of the need for upgrading all access points, for example, in the world. So why should you do it? Okay, and it's very difficult because it's distributed. If I would have this solution, actually not this, but the other for network function virtualization, all the people were saying, that's great, it's a new functionality, just give us the code, we plug it in, and it works. Okay, so the reason, what I see personally as an advantage in this is that they are trying, the people behind SDN and network function virtualization are trying to provide a framework that is much more flexible than before, okay? So it can do the things that were feasible before, plus other things, okay? So I'm not saying that before it was not possible to have QoS, but that before it was more specific. So you needed a real expert for that hardware, for example, to run it properly. In perspective, of course, if they will fulfill all the things that I was saying, it's not yet exactly everything mature on this framework, okay? Then probably we could do the same things and maybe also enable faster innovation, okay? To be fast in developing new solutions. That is the major benefit, okay, of virtualization, things like that. Because of course, maybe in some cases you don't need virtualization per se, but you will see that the system becomes so flexible that why not, okay? But it's my personal, okay, the reason why personally I'm working on these things. I see a good perspective, but of course the purpose here is to present you an idea, okay? So are there any other questions? Okay. Yeah.
So you said controller tray is really detailed, like the whole network would be forecast.
It's another good point. In the version that I was presenting you, because it's the traditional way to present SDN, there is a central controller, okay? Centralizing functionality in the networks becomes, let's say, similar to saying I generate a bottleneck and also a single point of failure, as you were saying. Actually, I don't have material in the presentation, but there are groups of people that are studying how to make it reliable and robust. The simplest way that comes into my mind, which is also connected to the next part that we see, is that the controller itself can be a virtualized function. So you can have an environment in which the controller, since it's a piece of software, it's a virtual machine, and as a virtual machine, you can have duplicates, for example. So you can build your system in such a way that you have two mirrors, or three if you want, of the same controller, and they operate in parallel. When one fails, the other gets retrieves, and so on. Okay. However, that is one of the points. As I was telling you, the security, also in terms of potential robustness, let's say, to attacks, anyway, is one of the problems on any new technology, because, as I told you, basically they secured the interface between controller and the switches. But there are, of course, several cases in which there can be attacks. So a fake controller can try to do something, or switches can misbehave. So that is something that is people expert in security. I think that is a big, I'm not an expert in security. For people that are expert in security, that is a very promising field, because to make SDN real, of course, you cannot say, oh, my controller can fail. Okay, that's okay. Your network will be down for 1 hour until you run again. It must be embedded with this thing. There is the potential, because when I will show you the other part, which is network function virtualization, you can merge them and it becomes much better. But it becomes also a very complex system. Okay? The network function virtualization is much more complex than this. Okay? But it's a good question. That is an open problem. If you go in the literature, you will start to see hundreds of papers on this.